Okay, so welcome back for the second talk, which will be on Instantons and Monopoles by Sergey Cherkis from the University of Arizona. So this will be the second talk, and as I understand, will be on the more mathematical aspects of the theory.
Thank you. So, as promised, this will be a mathematics talk, but the subject is the same. Though we'll cover somewhat different material. So first, there is this observation. I'm not sure how early to track it, but it certainly appears in the paper of Donaldson and probably earlier, is that if you start with self-duality equations on R4, well, you can write it this way, and you can write it quite explicitly. If you chose some trivialization, then you have this one formal connection, that's your curvature, and you can write it in terms of components if you wish. Then you have three equations. And you might now, instead of looking for instantons, which have finite action, you can first explore the equations themselves and look at connections which are invariant with respect to translations in one of the directions of R4. As a result, you will get a solution on R3, which depends on the remaining three coordinates, and is independent of, let's say, zero direction. Then if you call minus A0 phi, then these equations become what's called Bogomolny equations. Now, you can continue this process, and if you impose independence of the two directions, let's say direction 3 and 2, then these equations reassemble into Hitchin's equations. And if you impose independence of the three directions, you'll get one of the most beautiful integrable systems I know, systems of Nahm equations. So it consists of three matrices, A1, A2, and A3, such that covariant derivative of one is a commutator of another. So three matrix-valued functions which depend on one parameter S. And then, I guess, analog of all these in zero dimension is the system of ADHM equations. And another marvelous observation by Atiyah, Hitchin, Drinfeld-Manin, Nahm, and people who extended this, is that there's a relation between various solutions in different dimensions. For example, initial ADHM transform relates zero-dimensional data, some matrices satisfying algebraic equations, to instantons or solutions of these equations on R4. Nahm discovered that there is a transform relating solutions of Nahm equations to solutions of Bogomolny equations. That is his construction of monopoles, which we're about to review. Similarly, given Hitchin system, well, a lot in this depends on boundary conditions, but schematically, the transform that was explored by Szabo transforms back to another solution of Hitchin system of different rank and different boundary conditions. There are more sophisticated versions of these transforms which take into account various possible boundary conditions and other backgrounds. So another useful observation is that these three equations, in all of these cases, it's a system of three equations, they're intrinsically quaternionic. So let's look at quaternionic units. We'll denote them E1, E2, and E3, and they satisfy these famous relations written by Hamilton. Now, a quaternion is an object which has this form. It has four coordinates, Q1, Q2, Q3, and Q4, and it is this combination of identity and quaternionic units. Now, quaternionic conjugate has this form, and these quaternionic units admit a two-dimensional representation. You can represent them as 2x2 anti-Hermitian matrices acting on two-dimensional space, which will denote S. Now, for physicists in the audience, one of the such representations is -I times Pauli matrices, if you like. So for concrete calculations, you can write them out. Now, if you are given a connection on some Hermitian bundle of R4, then you can form a Dirac operator by taking covariant derivatives in corresponding directions and combining them with corresponding quaternionic unit. So if you like, from this point of view, Dirac operator is a quaternion whose components are covariant derivatives. Now it has a Hermitian conjugate, given here. Hermitian conjugate of any of these dj's is minus dj, and quaternionic units are anti-Hermitian, and, well, identity map is Hermitian. So that's the conjugate operator. So here's the observation that is at the heart of all these transforms, is that if you take a Laplace type operator here, d star d, then it is an honest Laplace operator, covariant Laplacian, plus something which is quaternionic, and the combination here is exactly a combination which vanishes if the connection is self-dual. So saying that connection is self-dual is equivalent to saying that this combination is quaternionic real. It commutes with all quaternionic identities. On top of it, once it is real, it is it is non-negative. And if your connection is non-trivial, then you can also say, or without flat factors, then you can say that this operator is strictly positive. So that's a very important condition in all these transforms. Okay. It's strictly positive simply because this is a Laplacian, and if connection doesn't have covariantly constant sections, then this is strictly positive operator. Now also, this imaginary part of this combination has a different interpretation. So in beautiful lectures by Hitchin on Dirac operator, there's this observation that imaginary part of this combination is a moment map of gauge transformations acting on the space of connections. Now, let me illustrate this in the case of Nahm equations. So I'd like to emphasize that in all these reductions that we considered, these covariant derivatives have different meanings. For example, for Nahm equations, this would be an honest covariant derivative, while this will be just matrix-valued functions. And for Instanton, all these are covariant derivatives. But in all of these cases, you are dealing with some infinite dimensional hyperkähler space and hyperkähler reduction on it. So let's look at, in particular, at the case of Nahm equations. So as I mentioned, here we have quadruplet of Hermitian-valued matrices, if you pick a particular trivialization of a bundle. So you start with an interval or a line, you have a bundle over that line, it's trivial, you can choose a trivialization of that. Then your connection can be written in this form, and you have three bundle endomorphisms, T1, T2, T3. So you have this quadruplet. Now, by itself, this quadruplet connection and three endomorphism, it forms an affine space. And if you look at a tangent space at a particular point, that can be identified with quaternions. And it has a natural norm. So as a result, you get an affine hyperkähler space, meaning that it has a metric, it has three complex structures. You can multiply delta t by E1 or E2 or E3 and get a new one. And moreover, this space has an action of a gauge group, which acts like this, which respects the metric and commutes with action of by multiplication by E1, E2, and E3 from the left. So that means it is triholomorphic. So once you have this, you can perform a hyperkähler reduction, just as a symplectic reduction. You can write the moment map for this action, and the moment map equations are exactly the Nahm equations. So Nahm transform consists of finding a solution to Nahm equations, fixing that solution, and then from that solution, forming a Dirac operator. Not just one Dirac operator, you can form a whole family, parameterized by a point in R3. So this combination is now, as I mentioned, family of Dirac operators. So if you solve a Dirac equation, the solution depends on t. So if you like, if you look at the kernel of this operator at any point t, as you vary t, the kernel will change. And this kernel is a sub-bundle in the bundle of all L2 functions on the interval of all sections. So as a result, it will have an induced connection. So this connection is written here in explicit form. Right, so if you form an orthonormal basis of solutions, then you get a connection, a matrix acting on this basis. In addition to this, you get an induced endomorphism on this kernel bundle, because S, multiplication by S, still gives us another L2 function on the interval, and you can project back. So the magic of Nahm transform is that if you started with this solution, go through this process, and induce connection and endomorphism, this pair phi and A will solve Baumik equation. It will be a monopole. Let's compute through one example just to see how details work out. Consider a rank 1 case. So all our matrices are 1 by 1. And we'll look at these on a semi-infinite interval, on array from lambda to infinity. So then Nahm equations are these. And because all t's are 1 by 1 matrices, they commute with each other. So all the right-hand sides of these equations are 0, and that means that t1, t2, and t3 are just constants. So we have this constant triplet, and then we have also our parameters, point in R3. This is the point at which we will be computing our monopole fields, if you like. We'll vary that point. So there's a little t's. So if you like, this solution of Nahm equations that we chose will be a position of a monopole. This little t will be position of a point at which we are going to compute monopole fields. And what will be significant in our story is the difference of the two, right? Because it's that difference which entered the Dirac operator. So let's call it z. So now this twisted family of twisted Dirac operators is simply DDS minus sigma i's times z, sigma j's times zj's, or z slash in physics notation. And we want to solve this equation. Well, this operator is constant. I'll call it z slash. So the solution psi has a form of some normalization constant, e to the z slash times s, times some two-dimensional spinner. I'll call it zeta. So in principle, you can have, well, it's two-dimensional space, you have a pair of solutions. Next, what's important is for us to ensure that the solutions are L2 on the corresponding interval. Well, if you look at this operator, well, it has two eigenvalues, z and minus z. Depending on which one you pick, you will get either solution which exponentially grows or exponentially decays. So if you put an eigenspinner corresponding to minus z eigenvalue, then you get solution which exponentially decays to the right, and it is L2. Okay, so we're looking for L2 kernel of the Dirac operator. So once you've found that solution, it basically looks like the spinner. So you find eigenspinner of this, that's zeta, and the prefactor becomes e to the minus zs. Next, you need to normalize it. You find normalization factor by just integrating square of that. And from this, you can compute right away what the Higgs field is, for example. Well, it will be integral, the definition of phi was integral of psi dagger psi times s. So in our case, it amounts to this. Fairly straightforward calculation gives you this solution, which is exactly the Dirac monopole. Now, I did the calculation here only for phi. You can compute A by the same token and get the explicit expression. So next, getting some more interesting solution, we can look at the same problem, but on an interval. So let's look at on an interval minus lambda lambda. The equation is exactly the same. T is still constant. You have the same equation. You have this solution. Except now, we don't have to deal with exponential growth. Either of the two solutions that we had are L2. So we have two independent solutions. Let's assemble them into a matrix. So this psi, the first column will be one solution, second column will be another. So then this is exactly a basis of solutions with some normalization factor. And by computing psi dagger, you can easily find the normalization factor. Now you again are faced with a very simple integral. You compute that and you find the Higgs field. And similarly, by the same formula that I've given before, you can compute the connection. Yeah. Yes? Well, there are two gauge groups at play. There's gauge group on the line acting on T's, and in all these cases it was rank 1. And then there was a rank of the resulting connection. So that rank is the dimension of the kernel. And secretly, it is all incorporated at conditions at these endpoints. So in this example, the rank was simply the number of the finite endpoints in the story. It's a little more complicated in general, is that you have to specify the behavior of these matrices T. So if T is a higher rank, you have to specify behavior at this lambda point. And in fact, so let's look at an example. Suppose that our T's are rank n. And we want to solve something like this. And cyclic permutations of 1, 2, and 3. So let's look at for a basic solution which looks like something constant, some constant matrix, divided by some power of S. Well, you plug it back in, you see that on the left-hand side you get, let's say, rho 1 divided by minus alpha S, alpha plus 1. On the right-hand side you get comparing the powers of S on both sides, you see that alpha has to be 1. And that tells you the commutation relations between rows. So if alpha is 1, it tells me that minus rho 1 has to be rho 2, rho 3. And cyclic permutations. So up to multiplying these rows by I over 2, some factor like that, it tells you that rows form a representation of SU2. This representation of SU2 decomposes into irreducibles, and the sum of the number of irreducible components is the rank of the resulting group. So, in fact, it is common knowledge, but when we were dealing with this Bow transform that I'll be describing next, we couldn't find a place which had this theorem. So our next paper with Mark Stern contains this sort of one-dimensional index theorem that we prove. But this is well known in the community. Yes? It is entirely up to you. So you can choose which problem you consider for T's, and what I'm illustrating here is that that will lead you to a different instanton, a different monopole. So these boundary conditions determine the rank of the monopole, for example. Yes, yes, that's right. That's right. Well, T was a bundle endomorphism, so that is also a bundle endomorphism. Well, fiber endomorphism at lambda point. There are lots of other boundary conditions you can impose besides this pole, and probably the most comprehensive overview of possible boundary conditions is the set of papers by Gayotto and Witten. Well, that's what I was trying to illustrate here. You can imagine something wild, but if it is a Laurent series, then it has to start with one of S. So that is not the problem I'm addressing. We're not constructing monopoles, strictly speaking. We want to study instantons on Taub-NUT spaces. So just a reminder, so UN instanton is a pair, instanton on Taub-NUT is a pair of a bundle over Taub-NUT or multi-Taub-NUT space with a connection such that the curvature of that connection is first anti-self-dual and second has finite action. Now, when I say anti-self-dual, it means that I have to fix some orientation. I fix orientation this way, and it's not random. What's important for me is that underlying space has SU2 holonomy. Like it's hyperkähler, you can view it in one of the complex structures. Complex structures naturally, this complex structure naturally gives you some orientation of the space. It is that orientation in which the connection is self-dual. The reason that we choose self-dual instead of anti-self-dual is that this condition will ensure that the covariantly constant spinors of the underlying space correspond to covariantly constant spinors with respect to this connection. Or if you like that, in that complex structure, this connection will be holomorphic. Its 2-0 part will vanish. Yes? They are not Euler-Lagrange equation. Euler-Lagrange equation would be second order, but they are minimum condition for yes, they automatically solve that equation because of Bianchi identity. So every connection satisfies, so every curvature satisfies a Bianchi identity. Now, so this is Bianchi. That's automatically. And Young-Mills equation, or Lagrange equation, has a star here. You can see that if star f equals to f, or plus or minus f, it automatically solves this. But of course, there are other solutions of Young-Mills equations besides that. Right, so quick reminder of what Taub-NUT space is, or multi-Taub-NUT space. It's R3 with marked points, nu1, nu2, up to nu k. Then we write this function, and we have a circle fibered over complement in R3 of these points, and that has a metric given here. So that circle size shrinks to 0 at each point nu. And then there is a natural connection on that bundle, omega, which is given by one form dual to gradient of V. Well, this space already has something interesting on it, as I was trying to hint last time. Namely, it has some collection of abelian instantons. So each of these nuts, each of these points, nu sigma, has an associated line bundle carrying an abelian connection. Now, that abelian connection has two properties. So first, its holonomy around the tau fiber at infinity is trivial. So if you just look at parallel transport around the fiber, as you move to infinity, that parallel transport becomes trivial, becomes identity. And it also has first Chern number. If you integrate over the cigar originating from that point nu sigma, then, well, you get 1 if it's cigar corresponding to that nut, and you get 0 otherwise. In addition to these, there is a family of line bundles carrying an instanton connection. And that's the one that we derived last time in the example of getting instanton from a bow, getting Taub nut modular space as modular space of a bow. Now this, in turn, is slightly different. This one has holonomy and exactly parameterized by S, and its Chern class is proportional to S over L. So there's substantial difference between those connections and this one. This one is a whole family. You can multiply it by any number, and those are fixed. What's important is that if you combine all these together, if you take S equal to L and tensor it with all those other bundles, the result is trivial. So what it means is that now we can form a family, a one-parameter family parameterized by S of these connections. And the way we do it is, well, take a circle parameterized by S, let's say 0 somewhere here, and then write for a general point here, bundle L to the S with connection SA. And whenever you cross any of these P points that we chose to arrange here at will, then you tensor that bundle with corresponding R sigma, so with R1, for example, and that carries the corresponding connection. So basically, as we move along, we start tensoring with more and more bundles. And what's important is that when you go full circle, the bundle becomes trivial, and this connection becomes gauge equivalent to a trivial connection. That's right. So the point is that if S is equal to L, when you went all the way around, then you end up again with a trivial bundle. That's why this whole picture is arranged in a circle, naturally. What was ad hoc here is how we chose to position these points P. So as a result, we have many different families. Right? It's not canonical, and there is a question of which family is the best. Right? As Tolstoy said, all happy families are alike. Every unhappy family is unhappy in its own way. So we need to pick a special one that is for our purpose. So when S is not equal to L, you have non-trivial bundle. And on that bundle, we have this connection. So what we get is a family of abelian instantons. The arbitrariness in this family is how we position points P. So for example, if our S is within this interval, if it's here, then our sum here involves only A1 and A2, and it's on the bundle L to the S, tensor R1, tensor R2. Is that clear? As we increase S, we have to tensor, each time we cross a P point, we have to tensor with corresponding bundle R and add one more term here. Right, so we sum only over those R sigmas for which value of P is less than S. Yes? So you start here and you only have L to the S. Once you cross P1, now we're on the bundle L to the S, tensor R1. Once you cross another point, it is L to the S, tensor R1, tensor R2, and so forth. And this relation here, this triviality, ensures that when we go full circle, we end up back with a trivial bundle. That's why we want a circle. So at S, we are on a bundle L to the S, tensor R1, R2, some R sigma, so long as P sigma is less than S. So it does have this power of L. Right? If I don't include this L, the product of all these R's is not a trivial bundle. But this ensures that in the end, when S reaches L, I am back to a trivial bundle and I am on a circle as a result. Yes? Yeah? Importantly, L to the L and tensor product of all R sigmas is trivial. Yeah? So when in that formulation, when S becomes L, I end up with trivial bundle. It's the equivalent to S to the 0. So if S is equal to L, then I end up with this bundle. And that's a trivial bundle, which is the same as L to the 0. The small l. The small l was parameter in Taub-Knot, which was this. Okay, any other questions? Right, so now that we learned this, the formulation of the problem and some facts about Taub-Knot, let's get back to the question about what do we know about instantons on this space. So the very first question which we'll face in analysis is knowing how to deal with infinity. So dealing with infinity is a big part of the problem here. We'll be interested in kernel of Dirac operators. So we would like to know asymptotic behavior of the connection. So the first question is, if you do have an instanton on Taub-Knot space, for example, how fast does the curvature decay? What does the connection look like asymptotically? Well, Uhlenbeck proved that instantons on R4 have to have curvature which decays quartically. Well, how fast does it decay on Taub-Knot? Well, the curvature rate is very sensitive to the asymptotic metric and specifically to how fast the volume of the space grows. For example, to contrast with this result, Mochizuki proved that if you look at instantons on T2 cross R2, then in that case the curvature decays as well as 1 over R to the power 1 plus epsilon for any positive epsilon. So it can actually decay very, very slowly at infinity. So the first question we faced is what power of decay do we have for the Taub-Knot space? So first we prove something slightly more general but weaker, is that if you, instead of looking at instantons, if you look at any solutions of Yang-Mills with square integrable curvature, then it decays at infinity. Next, we impose a technical condition, which I presume can be dropped. Eventually, I think we'll drop it. But for now, let's impose this generic asymptotic holonomy condition. It states the following. If you're standing at some point on R3, there's a circle above it. You can parallel transport around that circle. That gives you the holonomy. And look at eigenvalues of that holonomy. And now, let's start moving in some direction R3 to infinity, and look what happens to these eigenvalues. So we presume that there is some direction in R3 in which these eigenvalues will have a limit, and they will all be distinct. In other words, our holonomy is generic in just one direction in R3. So these are theorems proved in collaboration with Andres Lara and Hubash and Mark Stern. So under this presumption, we prove that curvature of an instanton on taub knot with a generic asymptotic holonomy decays quadratically. So it decays as 1 over r squared. And moreover, this generic asymptotic holonomy means that this connection indeed has eigenvalues. The eigenvalues of the connection has limits in any direction in R3, and they're exactly the same in every direction. So if you are generic in some direction, then you are generic everywhere, and it's the same eigenvalues. They're independent on direction you pick. From this, we can extract the asymptotic form of this connection. So the statement is that there is a local trivialization in which the connection has this form that essentially the bundle splits into eigenbundles of the holonomy, and on each of these line bundles, the connection, well, is diagonal, and on each of these, it looks like one of these connections I already described. One of these Abelian instantons. So lambda is the limit of the holonomy, and m is what we call a monopole charge. So asymptotic infinity encodes some of the topological data, and that topological data are these charges, and I'll be more specific in a second. Next, because we'll be interested in Dirac operator, we need to make some statements about harmonic spins. So if none of these lambdas are 0, in other words, if asymptotic holonomy doesn't have invariant subspaces, then harmonic spinors solutions of Dirac equation have to decay exponentially. This exponential decay is dictated exactly by the value, absolute value of lambda. Now, if one of the lambdas vanishes, then they decay quadratically. And next, we prove an index theorem in this case. So index of the Dirac operator is expressed in terms of monopole charges and lambdas. So here, the floor of any real number is the largest integer not exceeding a, and this is the fractional part of it. So the index equals to the usual bulk term, which appears in Atiyah-Zenger theory, and the asymptotic term, which is computed explicitly. Because our manifold is non-compact, none of these terms separately has to be an integer for any reason, and it isn't. In fact, we'll compute this term later today. So the very first observation here is that index is continuous so long as this ratio, lambda over L, if you change these asymptotic eigenvalues, then index, well, continuous, that means it doesn't change, but it can change when lambda over L crosses an integer. In particular, if lambda crosses 0, changes from negative to positive, then index changes exactly by mj. Exactly. That's right. So this term changes continuously, and this term will induce the change. Yes. K is the number of centers of taub knot. It's taub knot K. And what's important is that when lambda changes, crosses 0, then index suddenly changes by m. You acquire extra m solutions. Now, we'll discuss in detail the meaning of this lambda and m and certain ambiguity, which is hidden there. It's important. Yes? So for a given instanton, of course, its index is a number, but now you can look at nearby instantons. You can change your asymptotic conditions. As you change which instanton you're looking at, you can change the index. And it changes exactly when lambda crosses 0, and one of the reasons is that your Dirac operator is no longer Fredholm if lambda is 0. So indeed the index can jump, but it was very important for us to see how it will jump. Any other questions? Allowed us to go from solutions of Nahm equations to solutions of monopole equations. So here is a generalization of that transform, which allows us to go, well, and vice versa. So Nahm formulated transforms both ways. It's like generalization of Fourier transform. You do it twice, you end up back with the same function. So Nahm formulated both transforms. Given solution of Nahm equations, you get solutions of monopole equations. And from solutions of monopole equations, you can get back to solutions of Nahm equations. I call them up and down transforms because one increases the dimension, takes us from one-dimensional system to three-dimensional, and the other from three-dimensional to one-dimensional. That's the down transform. So in our case, down transform will take us from an instanton, AE, to a bow. I'll describe what this bow is. And there is an inverse transform which takes us from a bow back to an instanton. So here's formulation of the down transform. As I mentioned, Taub-NUT is equipped automatically with Abelian instantons. There's k discrete ones, and there's another one which allows us to make a family. So I already mentioned this family of instantons on the family of line bundles. Now, if you give me a non-abelian instanton on Taub-NUT, A, on some Hermitian bundle E over Taub-NUT, we can now twist it by this family. In other words, instead of instantons on E, we can look at family of instantons on E tensor a line bundle, ES, this line bundle, and the natural connection on this is given here. There's connection A on E and connection AS on ES. As a result, we get a family, a one-parameter family of Dirac operators, DS. So each of these, for each value of S, is an instanton. But this instanton now has eigenvalues of holonomy at infinity, which depend on S. In fact, these lambdas, they change sort of linearly with S. It's lambda minus S, which will be asymptotic holonomy. Now we can compute the index. We'll call it R of S, integer-valued function. And this R of S is, well, integer and constant, except when we cross a lambda point, it can change. And we already know how it changes. It changes by M, the monopole charge at that point. So now that we have an index, we can have an index bundle. The ES will be the kernel of the Dirac operator. And that is exactly where this condition of positivity comes in. So strictly speaking, the index bundle is a virtual bundle. It's kernel minus co-kernel. But in this case, co-kernel vanishes. So we already argued that for anti-self-dual connections, this is strictly positive. So kernel of D, as a result, is empty. And it's only kernel of the dagger, which appears in the virtual index bundle. So indeed, this virtual index bundle is an honest bundle. It doesn't have any co-kernel. So as a result, for each value of S, we have a kernel, we have a space, and we put them together, you get a bundle over the interval, over our circle S. So as a result, instanton gives us a bow, what I call a bow representation. That is, our bow is a collection of intervals with arrows. Now above every interval, we have a bundle, E sub S. So let's outline how this works. So given an instanton, you can form a family, and then you can form a corresponding Dirac operator. Now, for each value of S, you get a kernel. So for each value of S, along this, so this wiggly interval signifies S, circle S interval. And so long as you don't cross any P point, you have this continuous variation of a bundle, and you have a kernel. If you cross a lambda point, the dimension of the kernel might jump. So for every S, there is a kernel. Next, if you're hitting a lambda point, then something important happens. So the power of decay of harmonic spinors changes. What's happening is also the Laplace operator here, which positivity of which was so important for us, suddenly develops a kernel. So this argument that I gave before fails at this non-Fredholm point. So let's take this into account, and we'll actually call this, we'll give a name to this space, kernel of L infinity or bounded solutions of Laplace operator. We'll call it W lambda. So that's the auxiliary space assigned to each lambda point. And now we can form an orthonormal basis of this space of harmonic sections, and similarly orthonormal basis of L2 solutions. Of course, when I say orthonormal, it's a different norm in both of these cases. So in this case, it is L2 norm, and in this case, you can pick some point, and at that point, take the product. So from these, we can find our T's essentially by the usual Nahm formulas. So you take multiplication by Tj's, coordinate in R3. This induces, this acts on the kernel and projects back on it. This produces endomorphisms of this bundle E, Tj's. T0 is the induced connection on it. Q will be the resulting map from solutions of the Laplace equation to solutions of Dirac. Right? If you have solutions of d dagger d f equals 0, then df automatically solves Dirac equation. So this combination is solution of Dirac equation. So that map from W to the fiber at this point we'll call Q. And you also have matrices which allow you to go across the P point. You can take solution at 1, take the spinor B corresponding to that point, multiply by it, and that is a map from fiber on one side to fiber on the other side. At the same time, if you give me some, so these T's will automatically satisfy Nahm equations, and they will satisfy some intricate system of conditions at lambda points and P points, which I'll specify in a second. At the same time, if you have such T's, which satisfy Nahm equations and these conditions, you also have up transform. It has the same flavor as Nahm transform, essentially. So given these T's and B's, form a Dirac operator, like so, which acts on sections of spin bundle tensor E of S. If you give me some solution like this, T, Q, and B, which satisfy these conditions, I call it solution of a large Bow representation. It's exactly that ES, which came from above. But now, given this, we want to find instanton on our space. So first, we need to parameterize our space. To parameterize our space, we use the fact that Taub-NUT itself is a Bow moduli space, but of a different Bow representation. As we discussed last time, if you have rank 1 here on an interval, and you have little t's, little b's, these are the maps, and little t's are constant across this interval. So that's what I call a small Bow representation. And it is here just to parameterize points on Taub-NUT. Moduli space of this Bow is a point on Taub-NUT. We'll be varying this. So what we'll do is that a large Bow representation with fixed t's and capital T's, Q's, and B's has its Dirac operator, and small Bow representation with varying T's and B's has a family of its own Dirac operators, little d's. So what we do is we'll twist one by another. So just take pointwise, well, tensor product, and construct an operator which acts on spin bundle, tensor E of the large representation, tensor little e conjugate of the small Bow representation. The goal is to get a Dirac operator which now depends on a point on Taub-NUT, but in a fairly simple way, in a linear way, if you like. And now, given this family, we can look at its index bundle So we can vary the point on taub nut. That gives a bundle over taub nut. The kernel is a bundle over taub nut. It has an induced connection. And the statement is that this induced connection will automatically be an instanton. So there's 2 points to prove here. First, that it satisfies anti-self-duality equation, which is sort of a straightforward calculation. And next, proving that it decays the way it should. Right? And that involves some estimates of one-dimensional Dirac operator that I mentioned. So what is this object, bow, which comes from this index bundle? In this way, we don't have to invent it. It simply comes from the index bundle. So a bow, in this case, an A-type bow, is, if you like, comes from a circle diagram with some marked p-points that we chose. What you can do is, well, you can cut your circle at these points. This gives you a collection of intervals. Whenever you cut, you also draw an arrow from the left limiting point to the right limiting point. Okay? So this, the result, will be an A-type bow, collection of oriented intervals connected by arrows. Next, a bow representation. A bow representation involves first choosing some lambda points. Lambda points will correspond to holonomy eigenvalues. So these lambda points are chosen on the circle, and choosing an integer valued function which is continuous except across lambda or p points. And whenever it is continuous across a lambda point by accident, then we assign an auxiliary space, one-dimensional space, just C, to that point. We'll call it W lambda to remember which space it is associated with. So in terms of a bow, you picked some points on the intervals, and you picked integer rank on each subinterval. And if it doesn't change across a lambda point, there's auxiliary space there. So that's what I call a bow representation. Now, a bow representation has an associated affine space. It consists of space of this bifundamental data. So each arrow has associated with it a space of maps from one end to another and backwards. And that space is automatically a quaternionic space. You can act on it on the left by quaternionic units, E1, E2, E3. So it's just a flat hyperkähler linear space. Similarly, at this lambda points, there's auxiliary space W, there is a phi byte lambda, and there is maps from W to lambda and backwards. This also forms a linear hyperkähler space. And on each interval, there's space of Nahm data. I already argued that this itself forms an affine hyperkähler space. So if you take direct sum of all these spaces, that's an infinite dimensional space, which we call the data of bow representation. And that has an action of a gauge group. It acts on B by corresponding left and right action at P points, because it's mapped from one fiber to another. It acts on lambda in its fundamental or defining representation, and it acts on T as it acts on connection metrics and on endomorphism by conjugation. So this action is triholomorphic. It commutes with quaternions and respects the metric. The moment map of this action will give us exactly Nahm equations and conditions at the endpoints. So the hyperkähler quotient of bow data by the gauge group is the bow moduli space. And because the group is group of transformations on a trivial bundle over a collection of intervals, this is much easier to handle than instanton moduli spaces. So then the question is, what are these moment map conditions? And then the level set for this reduction should be chosen to be equal to exactly news, which are positions of nuts in the taub nut. Yes? Yes. Sorry, no. Lambda points are locations of D5 branes, and P points were location of NS5 branes. Exactly. That's always the case. It is because in T-duality, so if you simply have a D brane wrapped on a circle, after T-duality, to find the position of the resulting dp-1 brane, that position is exactly the monodromy around that circle. That's why lambda points are positions for D5 branes. NS5 branes are a little more subtle. Any other questions? All right, so in more detail, there is, well, one can write explicitly, if you wish, choosing particular bases of these spaces, what complex structures are, and what the symplectic forms are. So, right, every complex structure, together with a metric, gives you a symplectic form, and the symplectic form can be written fairly simply in terms of these Qs. If you arrange these three symplectic forms into an imaginary quaternion, if you wish, then you can write that in terms of Q fairly simply. And then you have a gauge group action. So as a result, it gives you a vector field, X. If you feed it back into omega, then it gives you the moment map. So it's differential of the moment map. So from this you can compute the moment maps. And if you like, the moment map, if you act on this fundamental object Q, then it's simply imaginary part of Q dagger. It's the traceless part of this combination of Q dagger. So you can compute it fairly explicitly. Now, at the same time, if you act by conjugation, if you look at bifundamentals, then they're fundamental either with respect to this gauge group or anti-fundamental with respect to that gauge group. So moment actions will be again vector part of B dagger or vector part of, I call them, well, vector part of those arranged in the other side. So the main point I'm making is that this makes at least Bow moduli space fairly tractable, and these are hyperkähler spaces, just as instanton spaces are hyperkähler spaces. And our main theorem in this story is that this transform that I described is not just one-to-one map, it's an isometry of the moduli spaces. So the instanton moduli spaces is isometric to Bow moduli spaces. So if you want to study instantons, you might as well, and the spaces, you might as well just study Bow. Now, I mentioned that there is certain ambiguity in these charges that I described. So, and this is discussed in terms of brane configuration in great detail in this Witten's paper. And here I'll try to describe it in gauge theoretic terms. So first of all, I spoke about holonomy eigenvalues, but these mu's, or asymptotic lambdas, were really logarithms of that. So as a result, each lambda is defined only up to an integer shift. Now, what about these m's? So one lemma we proved is that, well, if you have generic asymptotic holonomy, then each eigenvalue at point above, over a circle above point t, as t goes to infinity, tends to a constant, plus some correction, which decays as 1 over the radius. So, of course, from this definition, as I mentioned, lambda, of course, is defined up to a multiple of L, right, because we were taking log. But this term is defined unambiguously. It's coefficient of 1 over R decay. Now, if you compare with our asymptotic connection, you can see that there's a relation that basically take lambda plus m over t divided by L plus k over t and expand it, and you can see that there's a relation. So this theta, this term, which doesn't depend on any choices, is really a combination of m and lambda over L. So this combination is independent of any gauge choice. While changing your trivialization will change your m by some integer and change lambda accordingly. So now let's talk a little bit about infinity and what sort of gauge transformations we can have. So if you take some large ball inside of taub knot and cut it out, what remains is the neighborhood of infinity. And neighborhood of infinity in taub knot is a length space. It is a 3 space divided by zk. Well, let's check this for a second. Taub knot 1 is supposed to be topologically R4. Right? So infinity should be a 3-sphere. So indeed, it is S3 divided by, well, Z1. Well, so we want to know all possible line bundles on a length space. Well, length space is covered by S3. So whatever bundle you have, whatever line bundle you have of S3 mod ZK, pulls back to a trivial line bundle. Well, any line bundle of S3 is trivial. So if you pick some trivialization of that bundle, then ZK will act on that fiber. So it's just, these line bundles are simply fall into representations of ZK. So there will be K of them. How can we see which bundle it is in terms of our integers and charges that we have here? Well, if you change the choice of trivialization of your line bundle of S3 by acting with e to the tau tilde over k, so basically perform some gauge transform along your fiber, then lambda and m will shift. Lambda will change by multiple of L, or by L in this case, and m will change by k, simply from this formula. So this pair, lambda L, is defined up to these shifts. So one way to fix this ambiguity, for example, is to put all lambdas in the interval from 1 to L. But also, the fact that m can be shifted means that there's some significance in m mod k. So let's say that m hat will be representative of this equivalence class in the interval 0k. So the statement is that it's exactly this m hat which determines, so if you like, magnetic charge modulo k determines which bundle it is over the length space that we're dealing with. That will allow us to choose the best position of p-points. There's another topological piece in the data. These are the first Chern numbers. So you can simply integrate trace of f over each of these cigars. That doesn't have to be an integer, but from knowing our asymptotics, well, it has this form. It is sum of lambdas over L minus an integer. We can write that integer mod n. So we write it as some s in Z, and c, which is within, well, it's a representative of that class mod n. There is a meaning to these, is that these are essentially, like, I don't know what to call them, higher Stiefel-Whitney classes. They're abstractions to lifting PSUN bundle to SUN bundle. So if you like, if you strip off the trace part of the connection, then you get a PSUN connection instead of SUN connection, and these C's are abstraction to lifts. So you can relabel your nuts so that the C's are ordered like that. Once you have this collection of k numbers, each less than n, you can get a Young diagram out of these. Right? They are all arranged in order, so the length of the lowest row of the diagram will be C1, then C2, C3, C4, and so forth. It's a diagram which fits into k by n rectangle. Now, the right way to view this diagram is really not as a Young diagram, but as a path from lower right corner to upper right, as a path on a torus, if you wish. So identify top and bottom and left and right, and then you have a path on a torus. And then given this path on a torus, every horizontal segment labeled by lambda, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, and every vertical by p. That is exactly how you should pick positions of p's, and that's what I call a balanced bow representation. And the advantage of it is that for this representation, you will avoid rank jumping as you cross P point. The rank will be the same. It's not a disaster if it jumps, but in some ways, this is the simplest one to deal with. It minimizes the possible ranks of the Bow representation. Now, similarly, you have this magnetic charges at infinity, mod K, and they also give you some Young diagram, which is a priori different from the one we had before. And that also gives you some path, and that's what we call a co-balanced representation. And that instead prefers the lambda points, and from our point of view, it's not the most convenient one for the transform, but it's convenient for other purposes. So, for example, if you look at purely Abelian configuration which doesn't have any instanton or monopole, in non-Abelian instanton or monopoles inside, so it just has these monopole charges and Chern classes, in that case, balanced and co-balanced Young diagrams will be just transposed of each other. So if you like, non-Abelian part is encoded in their difference. There's something interesting happening when they don't coincide. Now, there's still one piece missing, and that's just the instanton number. Right? It is something which has to be encoded in the value of second Chern class. So since tau naught is non-compact, this value of second Chern class does not have to be an integer, and we need some other definition of instanton number that would be an integer. So let's focus on a simple case, just single-centered tau naught. Well, that is a contractible space, so the bundle over tau naught, any bundle over tau naught is trivial, and you can give a connection on it given by global one form. At the same time, on the complement of a compact set that is near infinity, we proved that there is some gauge transformation which puts your connection in this form, diagonalizes it. Well, this neighborhood of infinity, for case of tau naught, is contractible to S3. So, as a result, we have a map from some space contractible to S3 to UN. That's the gauge transformation. So if you like, it's the degree of that map, which is the instanton number. Now, here's a different definition, depending on point of view. So if you try algebra geometric approach, then this definition is more convenient. Alternatively, you can say that at infinity, the holonomy, since we have generic holonomy, split our bundle into line bundles. So at infinity, over sphere at infinity, we really have this orthogonal flag. We have a flag space. Right? Our eigenvalues were ordered 1, 2, 3, 4. So as a result, we have a flag space. This flag space has this form, and the instanton number again is pi3, right? It's the map. We're interested in homotopy of this map, so homotopy class. So it's pi3 of the flag space. That's again Z. So what are the topological numbers we have assigned? We had instanton number, which just defined. We have monopole numbers coming from infinity, and we have first Chern classes. So if we fix these, fix lambdas, we should be able to recover our bow. Now let's come back to the index, because when you first look at this formula, no number appearing here is really an integer. So it's not clear from this formula that indeed it counts in index. It has to be an integer. So let's compute it for a case of tau naught. Now, first, let's look at this bulk term, integral of f by Jeff. Now, itself, because it's given by a global form, it can be written as differential over Chern-Simons form, and because, well, it's exact, you can write it as integral over the boundary of some geodesic ball of radius r of Chern-Simons form, of that one form which was given globally. Now, if you perform some gauge transformation to put it in this diagonal form, then Chern-Simons form is not gauge invariant. It changes by the degree of that gauge transformation. That was exactly the instanton number we had. and the remaining Chern-Simons form is easy to compute because this AG is now diagonal. So we can compute it explicitly and have this bulk term. If you combine this with that expression for tau naught, you get this, which tells you that, well, you have degree, the instanton number, the index is the instanton number, plus contributions coming from these combinations. What's important here is that these combinations, m minus lambda over L, if you remember the formula involving ambiguities, is unambiguous. That doesn't change, that combination of, so m changes, lambda changes, but this does not change under any gauge transformations. If you like, you can write it in terms of this subleading term of the eigenvalue expansion. And also this combination is strictly positive. Right, so far I described just how to deal with moduli spaces, and that moduli spaces are isometric. But what if you want not just to study moduli spaces, but you want to study instantons themselves? So using this Bow approach, I computed explicitly example of one instanton on tau naught. Unfortunately, the answer is a little messy, still fits on one page. But let me give you a slightly different example where the answer is, well, answer came out as a surprise to me, very compact. So Kronheimer observed in his master thesis that if you have an instanton on tau naught, which is invariant under S1 isometry, well, then you can write it in certain gauge in this form, where A and phi are tau independent. And he also observed that if the curvature was self-dual, then it means that A and phi satisfying Bogomolny equation. Now, in this trivialization, which puts it in this form, S1 action at fixed points doesn't have to be trivial, it has some weights. And because of that, this phi can be singular. Right? You can see that, well, as we approach any of the nuts, then V blows up as 1 over R. So phi can blow up as 1 over R and still have nice connection. So phi can have singularities at the nuts. So as a result of this reduction, we don't get just the monopole, we get a singular monopole. This monopole with prescribed singularities at the nuts. Using usual Nahm approach, to do such a thing, to find a monopole with k singularities, you have to solve Nahm equations of rank k. Okay? There's some progress in that direction, but we don't know such solutions explicitly at the moment. So instead, using bows, it turns out to be quite a simple problem. If you look at, in terms of yesterday's brain configuration, what we are studying is a single D3 stretched between D5s, so that we are looking for SU2 monopole with k singularities. That means that there's k and S5s. In terms of a bow, it means that we have an interval instead of a circle with collection of p points on it. So we cut it, and that is our bow. This is what I call a Cheshire Bow, because it's a bow, it's still in a circle, but rank over here is 0. So we don't draw it. That's the cat. We only see the smile. So all the ranks here are 1. So indeed, solving Nahm equations on each interval is very simple. All these t's are constant on the interval, and then there are maps between them. So you find solution of this Cheshire Bow, and that has a Dirac operator. Then, to parameterize a point on tau naught, you insert this honest bow. That has its own Dirac operator. Then you twist one by another. For this family, you find its kernel. And from that, you can compute phi and A. So we went through this process with Chris Blair. And the result came out to be, well, as I mentioned, if you look at the Higgs field, it actually fits on one line. It looks very similar to Bogomolny-Prasad-Sommerfeld monopole, if not for this alpha. So alpha is a function on R3, which is defined by this expression. So T is our position, Tj is our position in R3 relative to the knot, to the jth knot, and capital T is the position of that knot with respect to the monopole. Okay, so to me, to be honest, this came after pages and pages of calculation with Chris, and I was surprised that indeed it contracted into one line. Right, so to conclude, now ADHM-Transform produces instantons on R4, Nahm Transform produces monopoles on R3, and now we generalize this to something which is organized in terms of bows and produces instantons on ALF spaces. I was only focusing in these lectures on multi-taub knot, but this story also works for D-type ALF spaces. Now, we proved that decay of the curvature is quadratic, and we computed the index. We proved the moduli space isometry. And also, you can use this whole apparatus to construct explicit instanton and moduli spaces. Right? I'll stop here.
It's on? Yeah. So there was the index of a Dirac operator, which and it jumped, right? You showed this part which didn't jump, and then this other part which jumped. So that's the Dirac operator on the moduli space of instantons on taub knot?
No. That is Dirac operator on taub knot on the instanton background.
Okay. Can it say anything about a Dirac operator on the moduli space of instantons on taub knot?
Well,
will we suggest something?
Has to be computed. It depends which operator. There's some ambiguity there. So there is a conventional Dirac operator in a particular line bundle which comes with it, and there is a modification studied by Moore and collaborators, for example, which seems to be more physically reasonable. But I didn't compute any of these indices yet.
More questions?
Is there some straightforward relationship between moduli spaces of instantons on ALF spaces and the ones on ALE spaces due to Kronheimer, Nakajima?
Yes, so that's a very interesting question. So one other motivation for studying this is, as I demonstrated, instantons on ALF spaces have additional charges, these monopole charges. In particular, you can look at a case where all monopole charges are zero. So in other words, every bow has a limit. You can shrink all the intervals to zero. If you look at co-balanced representation, then, well, limit of a bow will give you a quiver, and limit of bow representation will give you a quiver representation. But only in this case, only in co-balanced case. So indeed, moduli space of a bow has a limit. You can change the parameters, which takes that moduli space to moduli space of a quiver. That's right. However, this happens only if the representation was co-balanced. This is not generally the case. So there are more bow representation than there are quiver representations.
More questions? If not, let's thank Sergey again for an excellent set of lectures.